So last time we looked at categories, and we had some examples of categories. We had the category of monoids, category of sets, and category of preorders. And today we're going to look at functors.
Yes. Did we actually manage that? On the one hand, there is a category of monoids where the morphisms are monoid homomorphisms, but also each monoid is a category with one object where the elements of the monoid behave like the morphisms of the category, and the operation of the monoid is composition.
Yeah. And if we take one further step back, remember that the category consisted of objects, which we are drawing as
Yes.
So we call the category C, and then we're drawing little dots. These are the objects. And then between the objects, we have so-called morphisms or arrows, which we can think of as kind of like functions, right? And there's always an identity. And if I have two morphisms that line up in the middle, then I can compose them to get a composite morphism, just like I can do for functions, right? There's an identity function, and you can compose functions.
Right.
Okay.
And these pictures assert facts. This picture says that this arrow is the composite of those two.
Okay, so today we're going to look at what are the morphisms between categories, right? So just like we said, that the natural morphism between sets is functions, the natural morphisms between monoids are functions that preserve the monoid structure. We're going to look at what are the morphisms between categories. So these should be things that preserve the category structure in some sense, right? Because we always want to preserve the structure.
Yes, you should understand that it is in the nature of mathematicians to stuff things up themselves. So, of course, if you know what a category is, you want to have a category of categories. I mean, you couldn't, that's just irresistible.
So these things are called functors. So let's first go back to Haskell and see what a functor is in Haskell. Right. So here I have a Haskell file where I declare a data type of trees, which is either a leaf or it's a node consisting of a left subtree, some data from A, which is a parameter of the tree, and then a right subtree. And then I've pre-cooked the example tree because I don't want to do this live, saying that it's a node. The left subtree is another tree, which is just a 4 with then 2 leaves. And then the data in this tree is 5, and then I have a right subtree, which is another tree, and so on. And if sorry. Okay, and I can load this, and it looks like I get this dangerous error, but that's just because I haven't done the functor instance yet, right? So I put a hole here, except that Haskell is very much more verbose about its holes. And maybe I say this is undefined for now. Okay, and then I can run my int tree if I want, and I see that it's just the same thing, right? Because it's just data. But now if I want to take this tree full of ints and turn it into a tree full of booleans, for example, then I would declare a functor instance for tree, right? So then turn this back into a hole again. So I'm given a I have to produce a tree of B's. I have a tree of A's, and I have a function from A to B. Okay, so how would I do this? Well, I would pattern match on the tree. And in Haskell, I have to do this by hand. So it's either a leaf, or it's a node left, a right. Okay, then I have these two cases. I load again, then I have 2 holes. Okay, if I have a leaf, then I really don't have much choice. I can't make a node because I don't have an A. So I better send that to leaf. And I have some idea that I want to preserve the structure, so I'm going to send nodes to nodes, which means that this should be a node, and then I can do a recursive call the left subtree, I have something in the middle, and I can do a recursive call on the right subtree. Okay, and here I need a B, but I have an A, and I have a function from A to B. So I can apply the function here. Okay, and now if I fmap over my int tree with the function from int to bool, which returns true if x mod 2 is 1 and false if it's not 1, see what happens. So that was my int tree, and my odd tree says that 4 is not odd, 5 is odd, 7 is odd, and 42 is not odd. Right. So I've gone through all of my tree and just applying the function to all the data that's in the tree. And this is Haskell's notion of a functor. Anything
Yes.
to add?
Preserve superstructure, act on substructure is what's going on.
So you could say, okay, that's a useful thing to have, but actually this was invented 50 years before Haskell was invented. It's the concept of a functor. So let's move back to Agda, where we can. So in Agda, we can actually say what we mean by a functor exactly, right? So first of all, we can talk about functors between two different categories.
You've got this strange eta equality thing again.
Okay, I think we can safely get rid of that.
It's surplus to requirement.
Yes. So here we can talk about functors between two different categories. In Haskell, if you think about what happened, we had the fmap here goes from tree of A to tree of B, right? And trees are always types. So, and f was always a function. So in Haskell, functors are always on the category of types and functions, right?
Yeah, so the type constructor tree takes a type of elements and gives you a type of trees. And then fmap explains how to monkey with the elements, leaving the tree the same shape.
But in general, we can be a little bit more careful. So we don't have to have the same category. C and D can be different categories. And right, so then we need one way of turning objects of the first category into objects of the second one. And we need one way of turning morphisms of the first category into morphisms of the second one. So saying if I have a morphism from X to Y in C, then I should get a morphism in D, and it should go from whatever we translated X to whatever we translated Y to. Right?
Yeah, so this means that we have the means to translate the entire picture from which pictures that tell truths about morphisms in C are preserved intact as pictures which tell corresponding truths about D.
So let's say that we have something like this. So this is my category D. And now to give a functor from C to D means that I should first of all map all of the objects here into objects here. So I'm going to send this one to this object, and I'm going to send this one to that object, and I'm going to send this one to that object, right? So I don't have to hit everything here, that's fine, but I have to translate everything here, right? And secondly, I need a way to translate my morphisms here into morphisms here, and they have to line up with how I translated the objects. I can't send this morphism to this one because the source and target don't agree with the other translation, right? So I have to send this morphism to something that goes between these two things. So I can send it to this one. And I have to send this morphism to something that goes from here to here. I can send that to this one. And I have to send this one to something else, but I also would like to preserve the structure of composition, which means that after I've translated these two, I have no choice I have to send this one to the composite of these two, which meant this to be. Right. I'm first translating the objects, and then I'm translating the morphisms in a way that makes structural sense, so I can't send things to things that are unrelated. And secondly, I have to preserve the other structure, which is the composites and the identities. Right? Yeah. And so that's what this says. I have an action on objects. I have an fmap action on morphisms. And if I send the identity over, I get the identity. And if I send a composite over, I get the composite.
Yeah. So this shouldn't strike you as in the slightest weird, because you've been living with this all your lives. Think about why a map is any good for getting around town. It's like there are dots on the map that refer to places, and there are lines between the dots that represent paths or streets that you can walk along. And the reason why the map is any use to you is that the dots on the picture correspond to places in reality, and the lines on the map correspond to ways you can travel in reality. So what functoriality reality is saying is that there's a useful truth about this thing, or the useful truths in C transfer in a helpful way to somewhere else. You know, that the map actually, the diagram actually corresponds to reality. Every time we actually draw a diagram like this, we're giving a functor, because this picture here really is a category with these three dots as the objects and the actual arrows between them. To say, oh, this is a useful diagram that tells you something about mathematics is actually to give a functor from this three object category to the category C. So this, there's a picture which tells you about something real. Is stuff we're used to living with. Right. That's a useful intervention.
But it's certainly an intervention. Okay. So I think, at least to me, the idea of having the action on objects and the action on morphisms makes a lot of sense, right? Because if we want to translate from one thing to another, we better translate all the things in the first thing to the other thing. And the laws, why are they useful? Well, from a mathematical point of view, you very often need them to do other constructions. If we didn't have these laws, then there's many cool things we couldn't do, because we can't, I mean, it's a producer-consumer thing, right? That if you're asked to produce a functor, then you have to prove more things. But then if you give me a functor, then I can assume more things about it. And it's often very useful that it preserves the identity and so on. And from a more practical point of view in Haskell, for example, the identity law, which says that if you fmap over the identity, which if you go back to Haskell, what that means is that the f here is the identity function, and we're going to traverse the whole tree in order to just do nothing to all of the data in the tree, right? We're going to do identity of A here, and then we're going to do the same thing to the left subtree and so on. That could be quite a costly operation. Whereas if you know that you have this identity law, that means that you can replace all of this here on the left-hand side with just the identity function on the right-hand side, which is constant time. Right?
Yes. Instead of doing nothing individual by individual, you just do nothing.
So in that sense, it can also be practically useful to know that your functors really are functors, that they preserve identities. And I think Haskell will assume this. So it could replace a costly left-hand side with a cheap right-hand side, right?
Yes.
So if your thing is not actually a functor, then that's going to change the meaning of your program, which is bad news. Right? But the good thing about doing it in Agda is that you can actually prove that the identity law holds. So you don't need to worry about this mismatch. Right? And I think you can come up with a similar optimization for homomorphisms, where you have a composite, turning it fmap of a composite turns it into a composite. Right? Okay, so I did tree and fmap in Haskell. Why don't you do it in Agda?
Okay.
So I've already repeated the thing I did in Haskell.
Yes, so we've got leaves, we've got nodes. Okay, so it's a record. So I have to explain, first of all, what's the action on objects? So what's the thing that takes a set of elements and produces a set of trees? That's the type constructor tree. And now I have to say how to take element arrows and turn them into tree arrows. And because we're working in the category of sets and functions, the arrows are exactly functions. So this is the job done by tree map. Okay. And now I have to prove that tree map takes the identity function on elements. When you give it the identity function on elements, you get something which behaves the same way as the identity function on whole trees. So we're going to have to prove this equation, and we're going to have to prove it. The best we can do is to prove it pointwise. So we're going to have to use function extensionality, which you have called what?
Ext.
Ext. So you can see we're trying to prove that two functions are equal, and this axiom of extensionality allows us to say two functions are equal if they take equal inputs to equal outputs. It's kind of what we want. So if I say ext question mark and give it, my new goal says for all inputs x, if you map the identity, so for all trees, if you map the identity function across the tree, you get the same tree back. So now, what do I want to do? I'm going to have to do this by induction, and I'm no longer in a place where I'm able to access the left-hand side, so I'm going to have to introduce some sort of helper function, which I will just do at the top level. I could do it in a where clause, but I'll just do it here. Yes, identity for set across T is T.
So I would guess that there's two reasons why Connor typed that out rather than just copy it.
Yeah.
First one is that he wanted to call this T rather than little x.
Yes.
Second one is he doesn't know how to use my keyboard.
Correct. Let's stick it in the whole tree, map, id. Okay, so now we're in a situation where we've got the same goal, but now we can actually do left programming. Look at, because, I mean, this is straight up, why is it stuck? You know, the left-hand side is stuck because we don't know what T is. So once we get as far as actually allowing some reduction to happen, then the problem behaves sensibly. Got Right. And you can see marvelously that our induction hypotheses are going to get us all the way home. And what to do? There are several different ways to skin this cat. Kong 2 is almost, but not quite, useful. Or at least it's a bit annoying to do this with Kong 2.
Well, maybe it's good to show the way it's annoying.
Uh,
So remember, Kong 2 was the thing that said if you have a function of 2 arguments, and these arguments are equal to 2 other things, then the whole thing is equal. Right?
Kong 2, but then what I have to do, because is there a Kong 3?
I don't think so. But
Well, that's really annoying,
Yeah.
isn't it? Because, right, if I do Kong 2 on node, then I get something which talks about the left subtree and the element in the middle.
well, I think this is quite a good lesson, right? So
Sure.
we want this 3 argument thing to be equal to that 3 argument thing.
Yeah.
And they happen to
Already
really
agree
in the middle. So we have to manufacture a new function which differs in the 2 places we care about, right? Which we do with a lambda typically. So we 2 places where they are different. It's L and R.
Right, and now I've got something which says something useful.
Yeah.
So if I actually just stick in a pair of question marks at this stage, you will see that this goal is my left induction hypothesis. And that this goal is my right induction hypothesis. Cool. So we've shown that doing nothing to all of the elements is the same as doing nothing to the tree. Okay. Now what's next? We have to show that if we have a function from x to y and a function from y to z, so f and g, that doing one pass doing f to all the elements and then doing a second pass doing g to all of the results of doing f, we could do in a single pass by doing the composite of f and g. Okay, so again, I'm going to have to pull this. I'm going to need to expose f and g the way we did last time. So same trick. I wish I could see f and g because I know I'm going to need to talk about them. So I say, please make them visible. Right. And then I say tree map comp f g. Right. So I imagine the definition I'm going to write in a moment. You know, I say, I wish there was a thing called tree map comp that just did this. And then I say Control C, Control H, and it says, well, if that's what you want, you'll have to give it this type.
Control C, Control H. H for helper function.
And then...
It's already in your coloring.
Is it?
Yeah.
Wow. So if I just yank, that's amazing. And it's even pretty much what we wanted. That looks good to me. Tree, map, comp, F, G, O. It's not quite what I want. I've forgotten something. I want to do this pointwise.
Yeah.
Okay. So we want to do it pointwise. Again, we're going to have to prove this tree by tree. So I say ext, and now I say tree map comp fgt. Control C, Control H. Oh, hang on.
But you don't have
Sorry.
the T. You don't have the T yet.
I don't have the T yet. Maybe I'll just do this. Okay, and now I've got a tree. So I grab that. And I am going to change the name of the thing to T. And it's going to annoy me, isn't it? Because that's tree. And okay, so now I've got my goal lined up. First of all, I'll check that it's fit for purpose by shoving it in the hole. But it told me what would fit in the hole, so it's not a surprise that it fits. Okay, and then you can tell what's going to happen. It's going to work exactly the same way. You know, if we're playing why is it stuck, the left-hand side and the right-hand side are both stuck because we don't know what T is. So it's the same procedure as last year, the same procedure as every year. So base case just goes through. Step case, Kong to
You are allowed to look at the goal before you.
oh yes, I suppose I am. But yeah, you can see it's the same deal. We already line up perfectly in the middle. We're just rewriting by the induction hypotheses yet again. So that's same deal. Lambda LR arrow node L something R. Can't even be bothered to say what. Tree map comp.
Yeah.
Tree map comp FGL. Tree map comp FGR. Get in. Right. So the underscore is fine because once I'd fixed that it's node L something R, there was no choice about what the something was. It was the only possible thing it could be was the thing in the goal, which was G of F of A. Of course, I could have instead done this. So I did that by saying solve constraints, Control C, Control S. So if you click in a hole and there's only one thing it can possibly be, and you tell it solve constraints, it writes the code for you. So that wasn't not the same thing as Control C, Control A, which is think of something that type checks. It's even more specific than that. It's try and figure out what goes here because there's only one thing that type checks. So give me the thing that type checks. Okay, yeah. So we've got that that tree is a functor from set to set.
Yeah. So in some sense, we are now justified in using the Haskell version, right? Because we really proved in Agda that it was a functor. It preserves identities and composition.
Yeah, but functor in Haskell means only functor from sets and functions to sets and functions.
Yeah.
And there's other categories than sets and functions. So although the idea is pretty useful in Haskell, it's even more useful in real life.
Yeah. And that's exactly what we're going to look at next here, right? So let's see if we can come up with a useful functor from the category of monoids to the category of sets. And I'm going to keep this pretty simple. So I'm just going to forget the fact that a given set has a monoid structure. And these things are always functors, right? So I have a set with some structure, and the morphisms were functions that preserve the structure. Then I can always forget about the fact that I had this extra data and just keep the bare set, right? So this is called a forgetful functor because we're forgetting some information. Okay, and that's not a functor from one category to the same one, right? It's from the category of monoids to the category of sets. Okay, so let's see what I need to do in order to give this. Well, I have to give an action on object, I have to give an action on morphisms, and I have to prove that it preserves identity and compositions. So what is this? The objects of monoids are monoids, and the object of set are sets. So I need a way to turn a monoid into a set. Right. Any ideas? Well, I could always return a constant set here.
Yes.
my favorite sets, the natural numbers or something like this. And that would work, but it wouldn't do the thing I wanted it to, right? I want this to forget the monoid structure. So if I look at what a monoid is, well, it's a set together with an operation on it and a unit for the operation. So if I just take the carrier of the monoid, that's going to give me a set, right? So given a monoid M, I can take the carrier of M, which is a set. So I'm forgetting the fact that I had an operation on this set. I just keep the set. Okay, and then if I have a monoid morphism from X to Y, I have to now give a function from the carrier of X to the carrier of Y, because that's how I define the action on morphisms, on objects, right? But what was a monoid morphism?
It's a function on the carrier sets that behaves in a particularly
So it's a function from the between the carriers that preserves the unit and the multiplication. Right?
Yeah.
So if I just take the underlying function, that has the right type. And it's, again, kind of in the spirit of what I want to do, right? I want to forget about the fact that I had some more information. So let's say fun of f. That seems to work. Okay, so I've given an action on objects, just take the carrier, forget about everything else. I've given an action on morphisms, just take the function, forget about everything else. But for this to deserve to be called a functor, I have to show that this now preserves identity and composition. Right? But if you look what this means, it's going to be really easy because this category of monoids, the identity has as underlying function just the identity function, and the composition had as underlying function just the composition of the underlying functions. Right? So Agda is telling me that the thing I have to prove is the identity equals the identity. Well, that's easy. And here, the composite equals the composite. Right? So that's also just by referral this time. So that's often the case that if you come up with the right definitions for the actions on objects and morphisms, then proving these things are usually quite straightforward. Right? So here it was really easy. In Connor's case, we had to do these helper functions, but each helper function was just straightforward pattern matching on the same thing as before. Right? So if these proofs are hard, then that's usually a sign that something has gone wrong somewhere, and maybe you don't quite have the right definition. Okay, but that's our first example of a functor that is not just taking a set and giving us back a set. Right? It's taking a monoid and giving us back a set. And let's look at another example where, say here we forgot some information, but if there is some canonical way to enrich something with information, then that's often a functor as well. So this time I want to go from a set and I want to make a pre-order on this set. So remember, pre-order, these were sets with an order relation which was reflexive, and transitive, and we didn't want any proofs in this relation. So I want to take a set and I want to make it into a preorder. And I want to do this in a functorial way, right? So I can't just say that, well, I'm always going to take a set and then I'm going to return the preorder on the natural numbers or something like this. Right? So, okay. If it's not completely clear what this means, then it's sometimes helpful to just ask Agda what we need to produce, right? So again, we need to produce an action on objects, an action on morphisms, and they have to satisfy these two laws. So what do we need on the objects? Well, then we need to take a set and we need to actually produce a preorder. Right? And I've defined this with the name smallest order. So I have this idea that I want to make as few things as possible related in this order, right? While still making a preorder. So, okay, I get the set X. And then here I have to make a preorder. I don't quite remember what that is, so I'm going to case on the result and have Agda tell me what I need to do. So I have to produce a carrier, I have to produce an order, and I have to prove that this order is reflexive, transitive, and irrelevant. Sometimes also called propositional. Okay, so the carrier I want to be X, because the only other choice I could have would be to either have something fixed again, which would be boring, or I could try something like X arrow X or something like this, but that seems really strange, right? But I can hope to actually use X and just put an order on X, so that if you imagine the forgetful thing, I will get the X back, which could be nice. Okay, but then here I have to say when are X and Y related in this order that I'm now making up, right? Okay, and I want this to be the smallest possible order. So I could try and say that, well, they are never related, right? That's very small. So if I try that, say, to port some things for this. Okay, so I could say they are never related. But then here I have to show that this thing is reflexive, right? So I have to show that for every x is related to itself, which is quite hard if I say that nothing is ever related to anything else. So this is too small, right? So
you need something which is at least reflexive.
Yeah. Okay, so then I could try again.
Next guess.
What's the smallest thing that is reflexive? Well, equality is reflexive, right? So I can say that x and y are related if and only if they are the same thing. Right? And then reflexivity just turns into our familiar reflexivity. And transitivity, well, that turns into our familiar transitivity of equality. And is this propositional? Well, that's exactly what this uniqueness of identity proof says. Okay, so I've given a candidate definition. It works on objects by turning a set X to the order which is the equality on X. But now I also need to make sure that this works on morphisms. So given a morphism between sets, so a function from X to Y, I have to produce an order preserving function from the smallest order on X to the smallest order on Y. Right? So I get an F. I have to make a monotone map. I ask Agda, what is a monotone map again? It's a function which is monotone, okay? And monotone means that if X is related to Y, then this function applied to X should be related to this function applied to Y, right? And the display is a little bit weird because the function here is goal 0, which I haven't filled in yet. Okay, so let's fill in the goal 0 first. So here I have to give a function from X to Y, but I have a function from X to Y given, so I'm going to try to use that one. What else can I do? And then here, now the goal is a bit easy to see. So say that given X and Y, if X is equal to Y, then we want f of X to be equal to f of Y. That's just the Kong function. Right? conf. Right. So the fact that every function is an order-preserving function for equality is just the fact that every function respects equality. Okay, and then we have to check that this preserves identity and composition. So again, we have that this f map of the identity should be the identity. And you could think that you should use extensionality again, but actually this is an equality between these monotone maps, right? And we had a way to show that they were equal from last time, which said that if the underlying functions are equal, then the whole things are equal. And here now, again, we see that the underlying functions are easy, right? They are the same. And here, I think it's the same deal again. So I want to show that this F mapping the composite is the same as taking the composite of the F maps. And that's again an equation between monotone maps. I'm going to use EQ monotone map. And then I see that, again, this is easy. Right. So I took a set and I turned it into a pre-order in the most boring way possible, right? Saying that the only things related are things being related to themselves. And in a precise sense, this is the smallest thing you could hope for, right? Because you need reflectivity. So you need that things are at least equal to themselves, related to themselves. This is saying there's nothing more going on. Anything else to add?
No, I don't think so.
No?
I can see where we're going next. But
Yeah, I think this is a good time to stop for today.
goals 0, 1, and 2 are showing that functors, like functions, compose and have an identity, and that's going to give us that functors are the morphisms in the category of categories, which is kind of what we wanted in the first place.
Right. So an exercise if you're bored. So this was the smallest order because I only put things, related things that had to be related. You could also ask if there's a greatest order, right? That relates as much as possible. It's sometimes called a chaotic order on a set. But I'll leave that as an exercise to try to fill that in. So UIP stands for uniqueness of identity proofs. And it says that equality is irrelevant. So in other words, it says that if I have two proofs of equality, A and B, then they are equal. So there's at most one way to prove that two things are equal. It's called uniqueness of identity proofs. And this is provable in Agda by default. You can turn it off and you get a very interesting type theory. But especially when you're doing these kind of things, it's very convenient to assume that there is no data in an identity proof. But yeah, good question.
Yes, so you get UIP for free just by pattern matching. Right? So you've got an equality proof, you pattern match on it, it's REFL, there's only one of it. There you go.
Okay, any other questions? Nope.